All right, so the total change in the speed between 1.0 and 1.1. So the change in speed, anything about speed we're going to read off. So the change in speed, we are going to read off the graph. We'll clean this up. Between 1.0 and 1.1 seconds, the speed looks like it's about -5 is the velocity, and then it's going to be 10. So the velocity is going to change by -5, or the speed will change by 5 centimeters per second. Now, we know it's not 0 because the values are different. That change is not 0. 10 centimeters per second is really huge. That's 10 centimeters per second. Definitely doesn't change by 10. And 15 is a humongous amount. That's like from here to here. Definitely doesn't change that much. So we're left with choice B, as we expected. Question 7. This graph, we were told, is a position versus time graph. So we do our Oizerga. Our origin, 3, 2, 1, 0, 6, 4, 2, 0. So the origin is indeed there. We want to be careful with these kind of graphs that at first glance may be, that look like they might be 0. We want to really check to make sure there really is 0. And so that one is 0. So we're good there. The y-axis position in meters, normal. Time in seconds, normal. So we can read position time. The slope is dividing the axes, delta x over delta t, which is the velocity. And the area is x times t, which is meter seconds. And again, that's nothing. Now, just looking at this graph, we know the slope is the velocity. So if you notice what's happening to the slope, if we were to assign numbers and say that's 1, this would be bigger, 2, 3, 4, the slope, the velocity is increasing. Now, a curved xt graph, we probably now know just by on sight that it's acceleration. So we know it's accelerating. So let's see now the position time for an object being acted by a constant force. The average speed during the interval 1 and 2 seconds. Now, the speed is the gradient, but they're asking for the average speed. The slope to the tangent is going to be the instantaneous speed. So this is where it's helpful for us to pull out our definitions. The average speed is delta x over delta t, which is the total distance over the total time. So if we look at the total distance it travels in the first 2 seconds is 8 meters. And that's in 2 seconds, so that's going to give us 4 meters per second. 4 meters per second. Now, what we might guess if we did this like this is we might draw a tangent here, and we could see that this might have a delta x, a delta y, excuse me, of 16 over 2 seconds. So that means that velocity here is 8 meters per second, right? So that's the final velocity, which we know can't possibly be true. And if we look at the time at 1 second, and we were to kind of try to do a tangent there, like so, we might have, maybe 5 in 1.5 second, which is going to be 3 point something meters per second. So we've got like a 3 point something meters per second going to an 8 meters per second. Not that, not that. And certainly every velocity between 1 and 2 seconds is greater than 2. So that can't possibly be right. And these don't seem to make sense. But this is a case where we could easily be tripped up. But if we were to take the instantaneous velocity at 8, at 2 seconds, it would give us 8, which we can see is the maximum it could possibly be. Next one, 8. We have a velocity time graph, and we'll do our Oizerga. Origin. Aha, right there. There's the origin. So we have our positive values, our negative values. Our y-axis is velocity in meters per second, times in seconds, normal units. We can read the axes, velocity time, the slope, dividing the axes, delta v over delta t is the acceleration, and the area, v delta t, is meters per second times second, which is meters, gives us displacement. All right, so now we're ready to read the question. Sliding to the right along a straight line horizontal surface. All right, so we see a velocity of v0 equal to 4 meters per second. After 4 seconds, the velocity is 0. And then we see the velocity later it's going this way. It has a negative velocity. So this thing is slowing until it comes to a stop and then speeding up in that direction. That's kind of weird behavior. What is the object's displacement during the time depicted on the graph? Well, the displacement is the area. So if we look at this area here, we have a positive area. And if we look at the area here, we see that there is a negative area. And this is a 4 by 4. 4 wide, 4 high. That's 16. Half of that is 8. So we have a positive area. Over here, we have a minus 4 by 4. This is a 4 side. This is a minus 4 side. So we got minus 16 for the rectangle, minus 8 for the half. So the displacement, the total area for the area depicted is 0 meters. So this depicts an object starting here, coming to a stop, and going back and returning to its exact location. Our next question, another graph, which we love. Oi, Zerga. Origin, we see here. That's our 0. Y-axis, velocity meters per second. Axis, x-axis, time in seconds. Normal units. We can read the axis, vt. The gradients divide the axes, delta v over delta t, which is the acceleration. And v delta t, which is meters per second times seconds, is meters, is the displacement. Now, if we see the forest for the trees here, we can see the curve is kind of doing this, and then this, and then this, and then this. All the variation where it's not on is a little bit of uncertainty from experimental data. All right, so now, engineer the velocity of a car on a straight track at regular time intervals. So what this shows is it's got a velocity, and it's moving in a positive direction. It's moving in a positive direction. It's got some V0, which is equal to about maybe 1.5 or something like that, maybe 1.5. And then it's got a velocity of 0. And then it hangs out. It stays at the same position. And then it has a negative velocity. And it increases and increases and increases. And then it has a constant velocity again of -2. So we have acceleration that's negative as it's slowing down, and then we have it's at rest for a while, and then it accelerates again in a negative, has negative acceleration. The slope is the acceleration, negative slope, 0 slope, negative slope. So decreasing velocity, velocity staying constant at 0, and then we have negative acceleration, and a velocity staying a constant -2. All right, so the data shows during which following intervals did it return to its position? Well, if it returns to its position, that's about displacement. So if we look at the displacement here, we might estimate this to be about 3 seconds, and that's 1.25. And these two lines look like they're parallel to each other, the same slope. So then it should stand to reason that if we go another 3 seconds from here, about 8 seconds, that would give us a negative area equal to the other area. So the green and the yellow areas would be equal to each other. So this represents, the yellow area represents it coming out here. Then it stays still for a while, and then it turns around and heads in the other direction with the same acceleration. So we expect it to take about the same amount of time, or 3 seconds for a total of 8 seconds. When does it return? Between 3 and 5? No, it's at rest. Between 5 and 7? No, between 5 and 7, it's on its way. It hasn't gotten there yet. 7 to 10? That's here to here. Yes, that looks like it's right. 10 to 12, it's gone way past because that area is way more. Therefore, it's choice C. All right, our next question. We have two objects, X and Y. Accelerate from rest with the same acceleration. So we got this one accelerating in this direction, X and Y. Same acceleration. X accelerates for twice as long as Y. So let's say, there's this period of time T, it accelerates and it covers this delta x. Well, this is going to, well, x is going to accelerate for the same amount of time, but it's going to travel even farther. All right? So let's take a look at what this means. We've got x, they accelerate from rest. So our equation that would describe this is 1/2 at squared plus v0t plus x0. We can make these both x0. From rest means the v0. So we're looking at an equation of xx is 1/2 at squared. And xy is 1/2 at squared. So let's say y traveled with a delta t equal to t. And we know x then travels with a delta t equal to 2t. So let's see what that means. T, instead of being t, is 2t. And remember, it's in parentheses. So that gives us 1/2 a times 4t squared. So if we compare the two, this one has the 1/2 a, and this one has 1/2 a. This one's t squared, and this one's 4t squared. So xx will travel 4 times as far. Which is true of these statements? X is moving at the same speed as y. At the end of their periods. Well, if they're both accelerating, they're going to have the same Vy and Vx at the end of that time interval, but Vx is going to continue to accelerate, so they can't have the same speed. X is moving 4 times faster. Well, let's look at our velocity equations. Vx is at plus v0, and we said that they have the same acceleration, and t is 2t. Vy is at, and it's just t. So Vx is 2at, and Vy is at. So Vx is twice as large as Vy, not 4 times faster. X has traveled the same distance as y? No, we already saw that was 4 times. X has traveled twice as far? Nope, it'll have twice the velocity. X has traveled 4 times as far as y. So that's all the reasons why the incorrect are incorrect and the correct are correct.